Hi everybody, hope you're having a wonderful day. Today we're going to talk about significant figures and accuracy and precision. So every value that we have, that we record down, is limited by our measuring devices. Obviously, as time goes by, we develop more precise measuring tools, and so we get more precise measurements. And so scientists would like to have both accurate and precise measurements. Accuracy refers to how close a measurement approaches the true value. So how correct is your measurement? For example, if I have something that's 10 kilograms and I measure it and I'm really close to 10 kilograms, then that means that I'm very accurate. If I'm really far off, then I'm not very accurate. Whereas precision refers to obtaining a constant value. So in science, it's not okay to just measure something one time. We have to keep repeating our measurements and make sure that we are getting the same values. And so if you keep measuring it and getting the same value, that means that it's a precise measurement. Another thing, let's say that I have the substance that has a mass of 10 kilograms and I mass it on one balance and then I mass it on another balance. It should say 10 kilograms on the first one, it should say 10 kilograms on the second one. That would be precise. So let's imagine that you were shooting darts. So if you were both precise and accurate, then that means that every time you shoot your darts, your darts will land right next to each other and all in the bullseye. Let's say that you are precise but not accurate. So that means that your measurements or your darts go in the same spot. They are repeatable. Sorry, I had little technical difficulties with my stylus here. So if you are precise and not accurate, that means that your darts will all be in the same spot, but not close to where you want it to be, or to the true value, which would be the bullseye here. Let's say that your measurements are accurate but not precise. That means that, if you do 3 of them, let's say they would go there. So they're not precise, they're not all together, they're not the same. However, if you take the average of all of them, you would be right at the bull's eye there, so that would be accurate. Finally, if you have neither, that would be, you have one here, one there, another one there. So they're not precise, they're not together, but also they are not accurate either because they're nowhere near the bull's eye. So again, our measurements are all limited by how precise our measuring devices are. So for example, if you see a measurement written down as 15.7 centimeters, well, that last digit is really an estimate. That 0.7 centimeters is really an estimate. So it's anywhere really between 15.65 to 15.75, we'd measure as 15.7. So we need to know 3 sets of rules, 3 things that we would use sig figs for in the lab. So the first thing is rules for recording data you measured. So if I send you to the lab and ask you to measure some things, you need to record your data with the correct number of significant digits. Number 2, you need to be able to do calculations and record your answer with the correct number of sig figs. And then also, you need to be able to, when you're reading literature, like let's say you're reading your science textbook, when you see a number written down for you, you need to be able to tell how many significant digits there are. So we're going to start with when you go back to the lab and you're measuring, recording with the correct number of sig figs. So the number of significant figures here, when you are measuring things, is the number of digits that you are able to read with certainty from the measuring device plus 1 digit that you estimate. For example, let's say that you have this ruler and you're trying to measure the length of this object here. And so your measuring device, let's say that these are centimeters. Let's write that down, centimeters. So every little increment, the smallest increment that you have there, is 1/10 of a centimeter, right? And so for sure you can tell that, so this is 1 centimeter, this is 1.1, 1.2, 1.3, 1.4. So you can tell for sure that it's 1.3 something, because your smallest increments are 1/10 of a centimeter, so you can tell with certainty up to 1/10 of a centimeter. You know that it's 1.3 something for sure. Then you estimate one more. So, you know, looking at it, looks like maybe 1.3, I'm going to say 7 centimeters. Now that 7 is understood to be an estimate. So, you know, 1.36 would be okay. 1.38 centimeters would be okay. We understand when we write that down that the last number is an estimate. Let's look at a graduated cylinder here. So this is a graduated cylinder. This is in milliliters. And remember that when you read a graduated cylinder, the bottom of the meniscus needs to be at eye level here, and that's what you read. So for this one, you can tell for sure up to the milliliter. So each of these little increments are a milliliter. So you can say it's above, you can tell for sure that it's, you know, 32 point something. In this case, it's right on the line. You still need to estimate one more because your smallest increment is a milliliter, so you need to estimate to 1/10 of a milliliter. So in this case, it would be 32.0 milliliters. Again, if you say 32.1 milliliters, that's okay. If you say 31.9 milliliters, it's okay. The important thing is that you record your measurement with all the digits that you can tell for sure, plus then you estimate one more digit right here. Okay, now there is an exception to that rule. The exception would be if you have any digital devices. For example, if you have a digital thermometer or a digital balance like we have in the back of the lab there. Since it's digital, there's no way for you to estimate. You can tell, you know, like if it's between 3 and 4, you can't tell if it's closer to 3 or if it's closer to 4 because it's digital. So if you were to estimate, that's just, you know, that's just making up a number. And so when you have a digital device, the last number is actually the estimated number. So when you have a digital device, you just write it as is. You just record all the numbers that you see. I notice with So we just learned how to record our data when we make measurements with the correct number of sig figs. Next is the rules for reading and interpreting data reported by others. So if you're reading your science textbook, or if you're reading a number on the test and you're trying to figure out how many sig figs there are. There are many rules. If you already know how to do this, follow the rules that you have. There's like 5 or 6 rules that you follow. I like kind of a shorter method. So the shorter method is you check whether your number has a decimal place or not. Okay, so you ask yourself, do you have, a decimal point, not a decimal place, of course. So if you do you have a decimal point in your number? Do you see a dot? Okay, and so if the answer is yes, then you find the rightmost end of the entire number, and since you're at the right, you're going to look to the left until you reach the last non-zero digit, the last digit that's not a 0, so anywhere between 1 and 9. This digit and all the others to the left are going to be significant. Okay, so for example, this number right here, 12.050 liters, has a decimal point, and so what you do is you start to the right of the number. So you start at that 0 right there. Okay, and since you're at the right, you're going to go to the left. And you're going to keep going to the left until the last non-zero digit, which would be the 1 there. And so all these numbers would be significant. So where you started to where you ended, everything included. So the 1, the 2, the 0, the 5, and the 0. And so that would be 5 sig figs. Okay? If no, so if you do not have a decimal point, reverse the instructions above. So that means you would find the leftmost end of the entire number and you would look to the right until you find the last non-zero digit. This digit and all the others to the right are significant. For example, 230 kilograms. So that does not have a decimal place, so you start from the left this time. So you're going to start at that 2. And you're going to go to the right until the last non-zero digit. In this case, the 3 is your last non-zero digit. So from where you started at the 2 till where you ended at the 3, those are all significant, so that would be a total of 2 sig figs. This rule is sometimes called dot right, not left. That's kind of an easy way to remember it. And so dot means like a decimal point. So if you have a dot, that means you start at the right. If you do not have a dot, then you start at the left. So dot right, if you have a dot or a decimal point, you start at the right, go to the left. If not, then you start at the left and go to the right. Okay, let's practice the other ones there. So let's go to this one right here. It has a decimal point, so you're going to start at the right. And so the right of the number is this 0 right here, and you're going to go to the left until the last non-zero digit, which would be that 5. So that 5 and 0 are significant, so that's 2 sig figs. Next one, 12.24. So again, decimal place, so you start at the right. You go to the left. That 1 is your last non-zero digit, and so that would include the 1, the 2, and the 4. So that's 4 sig figs. Let's look at this example right here. So this does not have a decimal point, so you're going to start from the left. So you're going to start at that 1, and you're going to go to the right until you reach the last non-zero digit. In that case, that's that 1, and so there's only one significant figure. 1204, so you start at the left because you don't have a decimal point, and you're going to go to the right until you reach the last non-zero digit, which would be that 4. So that 1, 2, 0, and 4 are all significant, so that's 4 sig figs. Okay, so now we know how to record our measurements with correct sig figs. We also know how to read numbers and tell how many sig figs they are, or they have. Next is rules for calculations. And so there are 2 separate rules. There's a rule for addition and subtraction, and then there's a rule for multiplication and division. Okay, so we'll start with addition and subtraction. So it says in addition and subtraction, we consider the significant figures on the right side of the decimal point. This means that only as many digits are to be retained to the right side of a decimal point as the number with fewest digits to the right of the decimal point. That's very wordy. And so basically what they're saying is that your answer should have least precise decimal place. Okay, so what you do is you look at the numbers that you're adding or subtracting. So in this case, we're adding 4.345 and 23.5. So 4.345, that is precise to the thousandths place. The last sig fig is the thousandths place. 23.5, the last sig fig here is the tenths place. When you add these together in your calculator, you get 27.845, but we have to round this to the correct number of sig figs. And so this number is precise to the thousandths. This number is precise to the tenths. Which one is less precise? The one that's less precise is the tenths place. So then your answer should be to the tenths place. So it would round to 27.8. Let's look at another example. I'll write it right here. Let's say that I have 120 milliliters, and then I'm going to add to that 52 milliliters. It's a 2 there. Okay, so when I plug this in my calculator, or if you want to do it in your head, you get 172 milliliters. Then you want to round it to the correct number of sig figs. So you look at your 120. The last sig fig is to the tens place. 52, the last sig fig is to the ones place. So then you ask yourself, tens place or ones place is less precise. And so the tens is less precise, so your answer should round to the tens place. And so the correct answer would be 170 milliliters. All right, so that's addition and subtraction. Basically, you look at the decimal place is what you care about. You want the least precise decimal place. So, multiplication and division. In multiplication and division, the number obtained after calculation of two or more numbers must have no more significant figures than that number used in the multiplication or division. So, again, that's kind of wordy. Basically, what they're saying is answer should have least number of sig figs. For example, let's say that you are multiplying 4.3458 by 2.7, plug it into your calculator, you get this whole big number. So then, in multiplication and division, what we care about is the number of sig figs. We don't care about the decimal place, we just care about the number of sig figs. So, 4.3458, that has 5 sig figs. 2.7 has 2 sig figs. And so you go with the fewest sig figs, the least number of sig figs. And so between 5 and 2, 2 is less. And so your answer should have 2 sig figs. So then 11.73366 would round to 2 sig figs, so it would be 12. Okay, so main thing to remember here with multiplication and division, we care about the number of sig figs. You go with the least number of sig figs. With addition and subtraction, you go with the decimal place, the least precise decimal place. One thing to remember is that significant figures are made up to basically tell us how precise our measuring devices are, and so they are only applied to measured numbers. If you have a number that is not a measurement, then it doesn't really have sig figs. It has unlimited number of sig figs. For example, counting numbers have unlimited number of sig figs. For example, let's say I'm counting how many students I have, and there are 12 students. I can never have 12.1 students or 12.5 students. I either have 12 or 13 because I counted them. And so that number, 12 students, has an unlimited number of sig figs because I didn't measure my students, I counted them. So counting numbers have infinite number of sig figs. Or if you have a definition, for example, by definition, 1 meter is equal to 100 centimeters. So that does not apply to all conversion factors, but only ones that are defined. So when they came up with centi, they said that would be 100th of the base unit, and so that's a defined value, and so this 1 and this 100 have infinite number of sig figs, so they do not limit your sig figs when you're doing calculations. Okay, let's look at rounding. Most of you know how to round. So if you're rounding a number, if your following number is greater than 5, then you always round up. For example, let's say I have 11.7 and I want to round that to 2 sig figs, so that would round to 12 because that 7, which is following my number, is higher than 5. If your number to be rounded is less than 5, so for example, if I have 11.3 and I only want 2 sig figs, then you round down, so that would be 11. Now what if your number is 5? If it's followed by a non-zero digit, then you round up. For example, let's say I have 11.51. So I want 2 sig figs. And so I look at the number following my 1 there, and it's a 5. So then I check the number after it. If it's a non-zero digit, so 1 through 9, then you round up. So this would round to 12. Now, what if it was not followed by a non-zero digit? So what if it was just 11.5? Or if it was 11.50? Then this part is a little bit new. So let's say I have 11.5 or 11.50, and I want to round to 2 sig figs. So what you do is then you look at the number preceding that 5. So instead of looking at the 5, you look at that 1. If it's an odd digit, you round up. So then if I want this to be 2 sig figs, it'll be 12. What if that number was even? So let's say I have 12.5 or 12.50. If it's an even number, then you keep it the same or basically round down. So that would be also 12. I know this part right here is a little bit confusing. It's probably also new. The only reason why they do that is so that half of the time you round up, half the time you round down, so it kind of evens itself out. But basically, the way that I remember this is just keep the number even. So if it's odd, you round up to make it even. If it's already even, then keep it the same, even. One last bit to the sig fig rules. If you have scientific notation, if it's truly scientific notation, then all the digits that are in your number that is preceding the times 10 to the power, so your actual decimal there, all the numbers there are significant. So right here, for example, these are all significant, so that would be 2 sig figs. Okay, so now that we are done with all the rules, we want to practice some of these problems here. So if you could please stop the video and then try to answer these questions, and then when everybody's done, please turn the video back on and I will put the answer key. Okay, so here's the answer key. Please go through it and see if you got any wrong. So for number 1, I looked at dot right, not left. So if it had a decimal point, I started from the right, went to the left to the last non-zero digit. If it didn't, then I started from the left, went to the right to the last non-zero digit. For number 2, I think A and B are pretty easy. Number 3, you want 3 sig figs, so it is 390, but if you write 390 like this, then it only has 2 sig figs, and so either you put a dot at the end of it, or you can also turn it into scientific notation, so that would have 3 sig figs. I guess the last way that you could do it also would be to write it as 390 with then a bar on top. That's kind of an old way to show it, but you are welcome to use it. So the bar tells you that that is the last sig fig. You usually put it on zeros when you want to show that those are significant, but the other ones are not. For number 3, you want to watch out that when you do these, I think most of you know how to do scientific notation. The problem here is figuring out how many sig figs to use. So your number in standard form should have the same sig figs as your number in scientific notation. So this has 2, this has 2, 3 and 3, 2 and 2, 1 sig fig and 1 sig fig. So if you put zeros there, that would be incorrect. This one only has 3 sig figs. That last 0 is not significant, so this should also have 3 sig figs. This has 4 sig figs. That last 0 is not significant, so then also this has 4 sig figs. For this one, this is addition. So what I like to do is line them up like that, so the decimal point lines up, or you can just do it in your calculator. But this is the long answer that I get. For addition and subtraction, you look at the decimal places, and so this is precise to the hundredths place. This is to the thousandths place, and so the hundredths is less precise, so your answer should be to the hundredths place. And then the last one, this would be division, so you follow the division and multiplication rules. So speed is distance over time, so when I calculated it, I got this answer on my calculator. So then with multiplication and division, you look at the number of sig figs. So this has 4 sig figs. This only has 3 sig figs. So you go with the least number of sig figs, so you'd go with 3. So that's 0.663. Remember that 0 is not significant. So that's 3 sig figs right here. Don't forget your units. All right, hope this helps. You guys have a wonderful day.